Hey yo, it's me, Factor and Frank, showing you the differences between linear, quadratic, and exponential functions. Now here's a question. Why did the construction workers have to hire a geologist? Because they kept taking the marble for granted.
First vocabulary term is a linear function. That's any function that graphs to a straight line. They're most commonly in slope-intercept, point-slope, and standard form. So remember slope-intercept, y equals mx plus b. Point-slope, y minus y sub 1 is equal to m times the quantity x minus x sub 1. And then standard form, ax plus by equals c. Here you can see this right here. This graph is the graph for each of these particular functions. So if you wanted to figure out what the equation of this line was, each of these is just a different way of writing the equation of this line. Next vocabulary term is a quadratic function. That's an equation of degree 2 written in the form y equals ax squared plus bx plus c. So we've been dealing with this a bunch this particular chapter. You see some examples of quadratic functions here. Notice the exponent, it's degree 2. That's what makes it a quadratic function. Over here you can see a graph of y equals x squared, one of the quadratic functions. Now an exponential function is a function of the form y equals a times b to the x minus h plus k, where a is not equal to 0, b is greater than 0 and not equal to 1, and x, h, and k are real numbers. So here are some examples of exponential functions. Remember, there's exponential growth and exponential decay. So here in the blue we have exponential growth, here in the orange we have exponential decay. Remember, that's determined by whatever your b value is. If your b value is greater than 1, so like 2, or here 2 as well, you know you're going to have exponential growth. Whereas if your b value is between 0 and 1, like 0.5 or 1/5, then you're going to have exponential decay. Now let's talk about how to determine, is a function linear, quadratic, or exponential. So sometimes you'll just be given a table or a graph and you have to determine which is which. Is it a linear, quadratic, or exponential function? Let's talk about linear first. If you're given a table and if the x values have a constant difference, they increase by the same amount each time or decrease by the same amount each time, then your y values should increase or decrease by the same amount each time. So here, since our x values are increasing by the same amount each time, 1, you can see that our y values are also increasing by the same amount each time, 3. Therefore, this is a linear function. If you were to graph this, it creates a straight line with a constant slope. So that's how you know if you're given a graph. It's a linear function. You know it's a quadratic function if in your table those x values have a constant difference between them and your y values have a constant second difference between them. Now what does that mean? Well, it means if I were to find the difference between these y values, so from 0 to 1 that's 1, from 1 to 4 that's 3, from 4 to 9 that's 5, from 9 to 16 that's 7. So you can see the first difference is not the same, meaning that it's not a linear function. Otherwise these ones would be the same. This would be a constant difference right here. But let's find the difference between those differences. Between 1 and 3, in order to get from 1 to 3, that's a difference of 2. To get from 3 to 5, that's a difference of 2. To get from 5 to 7, that's a difference of 2. So you can see we have a constant second difference. And that will tell you that it's a quadratic function. Now, let's say you're looking at a graph. A quadratic function is pretty obvious. It's going to be a parabola looking like this. And if you have that U-shaped curve with a variable slope, that just means the slope always changes. It's not constant like a linear function. Then you know it's going to be a quadratic function. Now let's talk about exponential functions. So given a t-table like this, if you have a constant difference between the x values, and you check, you don't have a constant difference between the y values. Here, no we don't. And you also don't have a constant second difference between the y values. No, we don't. Check to see if there's a constant ratio between the y values. So here, I go 2 divided by 1. What does that give you? 2. 4 divided by 2. What does that give you? 2. 8 divided by 4. What does that give you? 2. 16 divided by 8. What does that give you? 2. There's a constant ratio between the y values, meaning that this is going to be an exponential function. That's how you tell whether a t-table gives you an exponential function. On a graph, you're either going to have an exponential curve going upward, signaling exponential growth, or it's going to be coming downward like that. So it's going to signal exponential decay. Sometimes it'll reflect over the x-axis, but we'll deal with that later on. Also, there's a horizontal asymptote. So here you can see this graph right here is approaching but never reaches the horizontal line y equals 0. All exponential functions have a horizontal asymptote.
What do cowboy construction workers use for transportation? Sawhorses! Ayo, example time.
Now example 1 says graph each set of points. Which model is appropriate for each set? So let's plot these points on the graph and see, is it going to be a linear function, quadratic function, or exponential function? So we plot the point -2, -3. So we go over -2 on the x-axis, down -3 on the y-axis, and we'll put a point. Then -1, 0, we go over -1 on the x-axis, up or down 0 on the y-axis, put a point. Then 0, 1, we go over 0 on the x-axis, up 1 on the y-axis, put a point. Then 1, 0, we go over 1 on the x-axis, up or down 0 on the y-axis, put a point. And then 2, -3. So we go over 2 on the x-axis, down -3 on the y-axis, put a point. And now let's draw a curve going through those points. What does that look like? That looks like a parabola to me. So this is going to be a quadratic function. Here, let's plot these points. So -3, 6, we go over -3 on the x-axis, up 6 on the y-axis, put a point. -1, 0, we go over -1 on the x-axis, up or down 0 on the y-axis, put a point. Then 0, -1, we go over 0 on the x-axis, down -1 on the y-axis, put a point. And then 1, -1.5. So over 1 on the x-axis, down -1.5 on the y-axis, put a point. Draw a curve going through those, and here it looks like we're going to have a exponential decay. So it's going to be an exponential function.
Why did the worker's phone have to wear glasses? Because it lost all its contacts. Hey-oh, you try.
Okay, doing the same thing. Let's plot these points. So -3, 8. We go over -3 on the x-axis, up 8 on the y-axis, put a point. Then -1, 6 over -1 on the x-axis, up 6 on the y-axis, put a point. 0, 5 over 0 on the x-axis, up 5 on the y-axis, put a point. 2, 3. We go over 2 on the x-axis, up 3 on the y-axis, put a point. And then 3, 2 over 3 on the x-axis, up 2 on the y-axis, put a point. Draw a line going through those. Ooh, that's a straight line. That means that this is going to represent a linear function. Last but not least, 1, 3. We're going to plot that. 1, 3. So over 1 on the x-axis, up 3 on the y-axis, put a point. 0, 0 is the origin. -3, 3. We go over -3 on the x-axis, up 3 on the y-axis, put a point. -1, -1. We go over -1 on the x-axis, down -1 on the y-axis, put a point. And then -2, 0. Over -2 on the x-axis, up or down 0 on the y-axis, put a point. Draw a curve going through those points. Looks like a parabola. Therefore, this is going to be a quadratic function. Now, example 2 says which type of function best models the data in each table. Use differences or ratios. So here we're given a t-table. Now, first, check. Is there a constant difference between the x values? That's what you should always check first. So here we go from 0 to 1, 1 to 2, 2 to 3, 3 to 4. Cool. Now, what I would do with your y values, always check the differences first. So is there a constant difference? Then is there a constant second difference? If both of those answers are no, then you're going to use the constant ratio. So then you divide. So first, is there a constant difference between the given y values? So from 0 to 1.5, we're adding 1.5. From 1.5 to 6, we're adding 4.5. From 6 to 13.5, we're adding 7.5. And then from 13.5 to 24, we're adding 11.5. Okay, so there's not a constant difference. Let's check the second difference. So from 1.5 to 4.5, we're adding 3. From 4.5 to 7.5, we're adding 3. And then from 7.5 to 11.5, we're adding 3. Therefore, there's a constant second difference, meaning that this table represents a quadratic function. Here, doing the same thing. So first, check the x values. Is there a constant difference between the x values? So 0 to 1, 1 to 2, 2 to 3, 3 to 4. Yes. So now we can check our y values. So here, let's do it. With our y values, we always check the difference first. So from -5 to -3, you're adding 2. From -3 to -1, you're adding 2. From -1 to 1, you're adding 2. And then from 1 to 3, you're adding 2. Therefore, there's a constant difference, and it's a first difference, meaning that this table represents a linear function.
Why did the worker's coffee cup call the cops? Because it was mugged. You try.
Okay, doing the same thing here. So first, check your x values. Here, we're going from -2 to -1, -1 to 0, 0 to 1, 1 to 2. Perfect, we're good. Now let's check the y values. So is there a constant difference? So if I were to subtract these, no, there's no constant difference. What about if there was a second difference? No, that's also not working. Okay, so then we check the ratio. Is there a constant ratio? So what is 0.2 divided by 0.04? Well, that's 5. What's 1 divided by 0.2? That's 5. What's 5 divided by 1? We know that's 5. And then 25 divided by 5? That's 5. So because there's a constant ratio between the given y values, then you know that this is going to represent a exponential function. Now part B, again, you got to check, is there a constant difference between the x values? So from -1 to 0, that's 1. From 0 to 1, that's 1. From 1 to 2, that's 1. And then from 2 to 3, also 1. Again, it doesn't have to be 1 every time. It could be 2 or 4, okay, as long as it's the same each time. Here, let's check the y value. So let's check the differences first. So from 1 to -1, you have to subtract 2. And then from -1 to 1, you have to add 2. And then from 1 to 7, you have to add 6. And then from 7 to 17, you have to add 10. Okay, so there's no common difference. Let's check the second difference. So from -2 to 2, you have to add 4. From 2 to 6, you have to add 4. And then from 6 to 10, you have to add 4. Oh, look at that. So there's a constant second difference, meaning that this table represents a quadratic function. Let's talk about modeling basic quadratics from a t-table. So if you are given a t-table and it wants you to write a quadratic in the form y equals ax squared plus bx plus c. So these are just going to be basic ones. What you want to do first is you want to find the second difference. So here we see that the x values have a common difference, so we're good to go. We can then check the first difference of our y values. So from 3 to 1, you're subtracting 2. From 1 to 3, you're adding 2. From 3 to 9, you're adding 6. And then from 9 to 19, you're adding 10. Now let's check the second difference. So from -2 to 2, we're adding 4. From 2 to 6, we're adding 4. And then from 6 to 10, we're also adding 4. Okay, so there is a constant second difference, meaning that this is a quadratic function. Perfect. So what we want to do, take that second difference and divide it by 2. That'll give us the a value of our given function. So here, our second difference is 4. If we divide that by 2, we get 2. Therefore, our a value of our quadratic function is 2. We then locate the y value where x equals 0 to get the c value. So again, locate the y value where x equals 0 to get the c value. So where does x equal 0? Here. What's the y value that corresponds with that? That's 1. Therefore, our c value is 1. Last but not least, choose a point besides x equals 0 to plug in and get the b value. So we can choose any point besides this one we already used. So let's choose 1, 3. We're going to take 1, plug it in for x in this function that we have here, and take 3, plug it in for y. Now let's simplify it. 1 squared is 1, times 2 is 2. 1 times b is just b, and then 2 plus 1 gives you 3. So we got 3 plus b is equal to 3. We then subtract 3 on both sides. We get b is equal to 0. So we plug in 0 for b. 0 times x is just 0, so we don't even have to write that middle term. We just get y is equal to 2x squared plus 1. That's how it's done. Now example 3, let's do another one and make sure you got the hang of it. So step 1, find the second difference. So first, is there a common difference between the x values? We're just adding 1 each time, so yes. What about the y values? Well, our y values, from 3 to 0, we're subtracting 3. From 0 to -1, we're subtracting 1. From -1 to 0, we're actually adding 1. And then 0 to 3, you're adding 3. Now let's check the second difference. So to get from -3 to -1, you're adding 2. To get from -1 to +1, you're adding 2. And then to get from +1 to +3, you're adding 2. So there is a constant second difference, meaning that this table does represent a quadratic function. So we found our second difference. Now we're going to take that second difference and divide it by 2 to get our a value. So what's 2 divided by 2? That's 1. So you could write 1x squared, or you could just write x squared, because technically it just means there's an invisible 1 out here. Now what we're going to do is we're going to locate the y value where x equals 0 to get our c value. So where does x equal 0? That's here. And what's the y value that goes with that? That's 0. So we're going to plug in 0 for our c value. So that makes that easy. There is no c value. Next, we're going to choose a point besides x equals 0 to plug in and get the b value. So let's pick a point. How about -1, -1? So we're going to take what we got so far, y equals x squared plus bx. We're going to plug in -1 for our y value, and we're going to plug in -1 for our x value as well. Now, what's -1 squared? That's 1. And what's b times -1? That's -b. So you end up getting 1 minus b is equal to -1. Now we solve for b. Subtract -1 on both sides, and -1 minus 1, remember those don't cancel out, it makes it -2. And then you can divide both sides by -1, you get b is equal to +2. So b is equal to 2. We take 2, plug it in for b here, and we get our function. Boom, that easy. Now let's talk about modeling basic exponentials from a t-table. So we just did basic quadratic functions, now let's do basic exponential functions. So if we want to write our exponential function in the form y equals a times b to the x from a t-table, what you're going to do first, again, you check to make sure you have a constant difference between your x values, and then you're going to find the common ratio to get your b value. So here, do we have a common difference between our x values? Plus 1, plus 1, plus 1, plus 1. Yes. So now let's check to see, do we have a common ratio between our given y values? So what's 0.2 divided by 0.04? Well, that's 5. What's 1 divided by 0.2? That's also 5. What's 5 divided by 1? That's 5. And then what's 25 divided by 5? That's also 5. Awesome. So we do have a common ratio. Now that common ratio is your b value. So we're going to take 5 and plug it in for b right here. Sweet. So the only thing that's left is to find our a value. Well, that's easy. To find your a value, you're just going to locate the y value where x equals 0. So where does x equal 0? That's here. What's the y value that goes with that? That's this 1. That's your a value. Simplify this if you want to. Here, this 1, you don't necessarily need to write 1 times 5 to the x. It's still just going to be 5 to the x. So your given exponential function is y equals 5 to the x, and you're done. Let's do this one more time to make sure we got it. So first thing we want to do is find the common ratio to get our b value. So in this case, we check to make sure we have a common difference between our x values. 1, 1, 1, 1. Yep, we're good. Now let's go to our y values. So what is 2 divided by 5? Well, 2 divided by 5 is going to be 0.4. What's 0.8 divided by 2? That is going to be 0.4 also. What's 0.32 divided by 0.8? That is 0.4. And then what's 0.128 divided by 0.32? Also 0.4. So we do have our common ratio. That's 0.4. That is going to be our b value. So we take 0.4, plug it in for b. Next, what we can do is find our a value by just finding the y value that goes with x equals 0. So we go x equals 0, there it is. What's the y value that goes with that? That's 5. So that's going to be our a value. So you take that, plug it in there, and that is going to be your given exponential function that is modeled by this t-table. Sweet. Now, our word problem says a conservation organization collected the data on the number of frogs in a local wetland, shown in the table below. Which type of function best models the data? Write an equation to model the data. So step 1 in a word problem, we're not scared, we can do this. Step 2, we need to define our variables. So in order to find our variables, we need to know what is the question asking. It's asking which type of function best models the data. Write an equation to model that data. That doesn't really help. Well, is there anything in the problem that could help us define our variables? Well, it does say that the organization collected data on the number of frogs in a local wetland. And if you look at our t-table down here, we see that there are years and there are frogs. Years is time, and time is usually the independent variable anytime you're given the t-table, because the number of frogs depends on what year it is, meaning that this would be the dependent variable. So years, we're going to say, is our x value. And then frogs would then be the y value, or f of x. Cool. So now what we can do is we can write our equation, because the whole point of this question is to figure out which type of function best models the data, and then write the equation that models this data. So first, which type of function best models the data? Let's determine. Between the x values, is there a common difference? Well, we're adding 1 each time, so yes, there is. What about the y values? Is there a common difference? No. Okay, is it close? No, not really. What about a common second difference? So if you were to do that out, no, that's not really close either. Okay, well, how about an exponential model? So is there a common ratio? Well, let's try this out. What's 101 divided by 120? Well, it doesn't go in evenly. It's approximately 0.84. What's 85 divided by 101? It doesn't go in evenly, but it's approximately 0.84. What's 72 divided by 85? Doesn't go in evenly. It's approximately 0.85. And then 60 divided by 72 is approximately 0.83. Notice the common ratio is not that common. It kind of varies a little bit, but just a little tiny bit. You're going to get that when you're dealing with actual numbers, because when you're dealing with a population, it's not necessarily going to fit exactly into an equation every single time and be perfect. Okay, population is messy. Numbers are messy sometimes. But here you can see that it's very close to 0.84 if I were to average this all out. So what I can do then is I can take this exponential equation, because we just figured out it's going to be an exponential, and then our b value is going to be the common ratio. So what would be the average of this common ratio? It seems like 0.84, because if I were to average those two out, I would get 0.84. So 0.84 is what I'm going to plug in for my b value, and then again my a value is just the y value that corresponds with x is equal to 0. So my x value in this case is the years, so that would be here, x equals 0. What's the y value that goes with that? That's 120. So I'm going to plug that in for my a value, and that is going to be the equation that best models this given data.